Welcome back, everyone. High-altitude pseudo-satellites operate in a region where persistent flight becomes possible, without entering orbital space and without encountering weather systems that disrupt conventional aircraft. Engineers classify these aircraft by their extreme endurance capability, which supports communication, observation, and research missions across large territories. Their altitude offers clear viewing angles and continuous signal paths, which provide stable coverage for remote users or scientific teams. Understanding the physical environment at these altitudes matters because air density, temperature variation, and solar intensity influence every subsystem. This introduction frames high-altitude pseudo-satellites as durable platforms built to solve challenges associated with long-duration aerial presence. Their relevance grows as demand increases for consistent monitoring and reliable communication links across regions with minimal ground infrastructure. Wing structure defines the practical limits of high-altitude pseudo-satellite endurance because thin air requires significant area to maintain lift. Engineers build lightweight composite spars that resist bending forces across wide spans while avoiding unnecessary mass. These spars remain stable during large temperature swings, which occur during transitions between day and night. Smooth aerodynamic surfaces reduce drag and support efficient airflow, which becomes sensitive to disturbance at these altitudes. Solar arrays embedded along the wing capture high-altitude sunlight with minimal scattering. Internal cavities house wiring and control linkages, which must remain vibration-free to preserve control accuracy. This combination of structural strength, lift efficiency, and integrated power generation supports stable operation during extended missions. Propulsion systems rely on electric motors paired with large-diameter propellers that generate thrust efficiently in low-density air. The National Renewable Energy Laboratory in Golden, Colorado, analyzes power management techniques that maintain stable performance when solar availability changes during the daily cycle. Motor components use conductive paths that move heat into surrounding airflow, which protects efficiency during prolonged operation. Propeller blades create thrust by sweeping large air volumes with controlled rotation, which suits the thin atmosphere. These propulsion elements handle climb phases and station-keeping tasks that maintain mission alignment. Energy regulation systems balance electrical output with demand to ensure continuous functionality as conditions shift. Please subscribe. Energy storage systems sustain nighttime operation when solar input becomes unavailable for extended periods. Lithium-based battery modules positioned near the aircraft's structural center maintain balance and reduce aerodynamic distortion. Engineers use insulated compartments that protect the batteries from extreme cold, which would otherwise reduce output or damage internal chemistry. Heat from charge and discharge cycles flows through conductive layers toward outer surfaces, where airflow removes excess energy. Monitoring circuits observe current movement and adjust charging behavior to preserve long-term reliability. When energy storage operates correctly, the aircraft maintains propulsion, control surfaces, and payload systems until sunrise recharges the reserves. Solar collection determines the effectiveness of daytime energy production because sunlight arrives with minimal atmospheric filtering at these altitudes. Engineers distribute photovoltaic cells across the wings to capture broad sunlight angles throughout the day. Electrical output flows into conditioning units that stabilize current for propulsion, system electronics, and battery recharging. Heat from solar absorption spreads through structural panels before dissipating into the thin atmosphere. This process must remain predictable because uneven heat distribution influences material behavior and wing stiffness. Lightweight, high-efficiency solar cells provide sustained daytime energy, which enables long missions and reduces reliance on ground support infrastructure. Control surfaces maintain stability in thin air, where aerodynamic behavior changes rapidly with altitude. Ailerons, elevators, and rudders adjust airflow patterns that influence pitch, roll, and yaw. The Fraunhofer Institute for Wind Energy Systems in Bremerhaven, Germany, studies airflow characteristics at high altitude to support stronger control authority. Engineers combine mechanical adjustments with subtle thrust variations to achieve fine orientation control. Pressure sensors positioned along the wings detect changes in airflow and transfer data to onboard computers, which calculate precise corrections. Stability becomes essential because communication relays, atmospheric research, or observation tasks depend on predictable aircraft motion. Thermal conditions shift sharply between daytime and nighttime, which influences material performance and electronic behavior. Engineers install insulation layers that slow heat loss during cold periods, while preventing excess accumulation during prolonged sunlight exposure. Conductive components inside the fuselage move heat away from sensitive instruments and distribute it toward radiative surfaces. Predicting these thermal patterns ensures that structural elements maintain consistent shape and that electronics operate within safe temperature limits. Reliable thermal management supports endurance by preventing stress accumulation that shortens service life or disrupts mission objectives. Payload stability determines mission effectiveness because sensors, communication devices, or research instruments must maintain consistent orientation. The University of Southampton in the United Kingdom studies lightweight stabilization mounts that protect payloads from vibration and thermal distortion. Engineers position payloads near the center of mass to avoid aerodynamic imbalance. Power and data routes run through shielded channels that reduce electrical resistance and limit heat buildup. Stable payload operation ensures accurate imaging, strong communication relay performance, and reliable scientific measurements throughout long missions. Navigation accuracy supports mission continuity because wind behavior changes quickly at altitude. Satellite receivers pair with inertial measurement units that provide continuous position data. Protective housings shield navigation instruments from extreme cold that would otherwise degrade performance. The Indian Institute of Science in Bengaluru, Karnataka, investigates stratospheric wind patterns to develop improved navigation responses. Data from sensors flows into onboard computers, which then adjust thrust or control surfaces to maintain station over designated regions. Reliable navigation enables stable communication links and consistent data coverage during extended flights. Structural durability influences long-term mission success because high-altitude pseudo-satellites encounter continuous aerodynamic and thermal stress cycles. Engineers use bonded joints along structural intersections to distribute load evenly without adding unnecessary weight. Vibration management features reduce fatigue in composite materials. The Polytechnic University of Milan analyzes stress accumulation during extended missions to guide material selection. Durable structures preserve wing shape and maintain secure connections between components, which prevents deformation during repeated temperature and pressure changes. Strong structural integrity ensures predictable behavior and prolongs operational lifespan. Electrical integration coordinates the relationship between solar input, battery reserves, propulsion demand, and payload consumption. Power management systems regulate current flow to protect components from overload or voltage variation. Wiring routes use low-resistance materials to maintain efficiency and flexibility under temperature changes. Safety circuits monitor electrical behavior and prevent conditions that could damage instruments. The University of Tokyo evaluates conductive materials that support reliable, long-duration energy transfer. Atmospheric behavior influences aerodynamic performance and energy usage throughout each flight cycle. Temperature gradients cause density variations that alter lift and thrust efficiency. Engineers design control algorithms that interpret sensor readings and adjust orientation or thrust to counter these changes. Morning and evening sunlight transitions affect solar collection, which influences decisions about climb or descent. Understanding these patterns supports efficient energy use and maintains stable station keeping. These atmospheric factors shape how the aircraft sustains its mission profile over long durations. Operational planning determines when and how high-altitude pseudo-satellites deploy for maximum effectiveness. Engineers analyze historical energy usage, wind behavior, and mission needs to establish flight paths that preserve battery reserves and maintain communication links. Coordination between onboard systems and ground oversight helps adjust decisions during unexpected conditions. Mission planning enables continuous coverage across research zones, observation regions, or communication networks. Effective planning strengthens reliability and ensures that these aircraft provide dependable service throughout extended operations. High-altitude pseudo-satellites offer sustained aerial coverage without the expense or complexity of orbital systems. Their capability to remain above weather while delivering consistent performance supports communication, observation, and scientific missions. Endurance depends on careful integration of aerodynamic structure, propulsion efficiency, thermal control, navigation precision, structural durability, and electrical coordination. These interactions create a platform designed for reliable, long-duration use across large regions. Their engineering principles highlight why high-altitude pseudo-satellites serve as valuable tools for modern aerial operations. Thank you very much for watching. Please like and subscribe.